Thanks, Inicio, for having me speak and to proselytize a bit. Things I'm interested in. So I will be the bearer of bad news in that one must say something about D modules to tell you what the first word means, but I will do my best to make this as painless as possible. That in my experience, people do not feel a lot of pain with the D module. So let me first tell you what this Bernstein-Sato polynomial is, and we'll do it in the most naive way possible, which is if I give you this and I ask you to take its derivative, you would tell me I take the 2, it comes down, I decrease the exponent by 1. My 2's will go up like always. Okay, so now if I put an s there, where s is just some random new variable, and I ask you to take this derivative, you would do your best to never think and to blindly follow the spirit. And so I would just bring the s down, and I would decrease the exponent by 1. And if you like, maybe this is relevant later, I could think of it like this if I was really precious about not letting my exponent change. Okay? So this is a very simple thing, but of course, if I have some more complicated polynomial, you can do the same business. So from this, you can imagine, let's just work in a polynomial ring to begin with. Let me take some f in here. Then I can write f to the s plus 1. I could hit it by some sort of differential operator. Let me be a bit more clear here, which is that, if I have f to the s, if I hit it by partial x plus s, I would again naively just think the s is just along for the ride. I do every naive thing I could think of. So this would just be, I have an s times fs maybe, and then this partial derivative, which I've decided I should write like this. So, and of course I could make the s and s plus 1 play the same game. So I could take f to the s plus 1, hit it by some differential operator, maybe with some s terms floating around. And I could hope I get back to f to the s at the cost of some error term, basically. I want my error term to be symmetric, which is that it's a polynomial and the s is alone. All right, so if this happens, this thing here is called the functional equation. And the minimal, I can look at, if I assume such a thing exists, which you should not, it's no reason to think such a thing exists. It does turn out it exists. But if I look at this, it generates some ideal in here. This is a PID, so it has some minimal monic generator. I'm going to take the minimal monic such f of s, and I'll call it the Bernstein-Sato polynomial. Okay. So this is the thing. I haven't decided yet whether or not I'll actually tell you how to interpret this in terms of D module stuff. We'll see how things progress. And hopefully you can imagine how this sort of definition goes. Yeah.
So you take minimal where you let p vary, or?
Yeah. So I'm looking at any sort of pair p and b that satisfy this relationship. And then this gives me the b's form some sort of ideal in this ring, and then I pick my favorite generator of that ideal based on there. All right, this is the thing. Maybe before I tell you why this is interesting, I will bravely compute some examples. Well, actually, I'll first tell you why this is interesting, and then I'll compute some examples. the theorem of maybe Kashimara and Lagrange. So let me start with something nicer, something more simple. Let's say that
Okay, can I say something? This statement says that this minimal monic actually appears as a BF of some in this collection.
yes. I mean, these B's, whatever these B's are, they form some sort of ideal.
Yeah, but okay.
The point is that, I mean, the point that's not, okay, so maybe what I should say is the theorem of Kashimara and maybe Bernstein and others such a thing exists. Right? I mean, if I put 0 here, that would probably work. I could put 0 on both sides. So there is something there. But the point is that there's some non-trivial guy there. So this is not at all obvious. And you should not think it's obvious. I mean, the way this proof works is one has to take some sort of logarithmic resolution of singularities and manipulate D-module stuff. But it turns out it exists as a pretty deep result. So let's just take for granted that this exists. And maybe I'll tell you some interesting properties of it.
Wait, maybe I missed that, but so you consider a fixed differential operator and let f vary, or the other way around?
F is fixed.
F is fixed, and for all differential operators.
Yes. Yes. So I'm only interested in a particular, if I care about a hypersurface, and I want to understand the singularities of this hypersurface, and this is a construction I do.
This differential operator is sort of is a polynomial, so it's powers of taking the derivative and
yeah, I mean,
and
this
constants and rest.
this PS lives inside the differential operators, something like this, where this is your favorite chief of differential operators or global or the Veil algebra. But yeah, because there's some polynomials and differential operators. Yeah. I'll give an example, some more examples. So maybe I'll just say this cares about the singularities. Or maybe BF of S cares about the singularities of your hypersurface in this case. So one fact is that maybe the first invariant you have of a hypersurface singularity is something called this log-canonical threshold. You could think of this as if you're a singular point, so many multiderivatives vanish, you have multiplicity at that point. One invariant you could pick is I just look at the multiplicity. Somehow this log-canonical threshold is a much more sophisticated generalization of this. So this log-canonical threshold this is sort of a very classical singularity invariant coming from birational geometry. This is equal to the minimum of I look at the zeros of this b function. I do this, I flip signs, and I take the minimum of that in 1. So this, whatever it is, you should think of this as sort of a birational invariant. That's encoding some very subtle data about my singularity. And it's coming somehow from this D module, this sort of thing involving a bunch of differential operators. Maybe I'll say that if I look at the jumping numbers, these are again some sort of thing involving these birational geometry and multiplier ideals and sort of invariants. Whatever they are, there's some numbers that say something deep about your singularity. These are contained in the roots of this thing. And maybe another example I'll give is that this log-canonical threshold, it's sort of set up in such a way that it's a positive number. It's between 0 and 1. That's why this 1 appears. In fact, if you read any of the more recent papers by like Popa or Sato, these other people, they really don't like the fact that this one appears. And somehow this is a disadvantage of the law canonical threshold. So in fact, maybe the more modern thing is you define something called the minimal exponent. Which is just the minimum of these numbers. It's the same as before, except I'm taking out this one bit. And this is something that can detect irrational singularities. And law canonical singularities, all these things. So maybe you don't know what all these words mean, but the point is I'm trying to put on the left all these very subtle birational things, and on the right, numbers popping out of this totally opaque object, and telling you they're somehow related, and trying to convince you that because they're related, this thing must be interesting. And in fact, I would argue that this part here, where somehow there are things that you don't know how to detect birationally, but you can detect more easily using this B function, shows that in some sense it's a bit of an improvement. Right? You can take as a definition of rational singularities that the minimal exponent is greater than 1. In fact, this could be a definition if you want. Okay, so the moral is that BS polynomial knows about birational geometry. Let me put also some other facts before I compute an example. It's a fact that if I take the zeros of this thing, they're always negative rational numbers. Yeah, there's no reason you would think this, but it turns out to be true. And another thing that should probably be more important than resigning to this tiny little section of the board is that if I take the zeros of this guy, so there's some rational numbers, I can take e to the 2 pi I of that rational number, so I can exponentiate this thing. Then I get the eigenvalues of the algebraic monodromy of the multiplier. Okay, so I don't want to explain what these words mean, but the Milnor fiber is some sort of hypersurface that's modeling behavior very close to a singularity, and you can walk around it. This gives some sort of monodromy action. There's some sort of algebraic thing this interprets on. Some that has some map of C vector space that has some eigenvalues. These are something people care about. And the reason I'm writing this here is that over here I had all this birational stuff, and here I have this thing that's like walking around monitoring stuff. And these are somehow from 2 different worlds, but this thing is somehow bridging between them. Okay, so this is trying to convince you that this, whatever this mysterious thing is, its roots have content.
Can I ask you something? So this connection only works for in the hypersurface case. So when you have when it's the vanishing of one single polynomial.
So this is an area of research. So I think the current state of the art, and this is like within the past year, I think has been established completely by Mustafa, Popa, and all their children, is that if I'm a complete intersection, you can play the same type of game. I won't tell you what the B function is there, but there's some candidate. And I think almost all these things are true. Like this analog of everything. Like rational singularities, there's some notion there. And then outside of the complete intersection case, it becomes very difficult. But I think the expectation now is that one can do this, but this is probably like 10 years away. I mean, I should also say all these results I've written here are from like the 70s or 80s. So what I just told you, like this is on the past couple of years. So these are difficult issues, questions. Okay. Useful is. Let me compute an example. Let's say f is x. Well then, what am I tasked with? I'm tasked with hitting this guy with some differential operator so that I get left with x to the s. There's sort of one obvious choice, which is I just take the derivative, and then s plus 1 comes out. So in this case, this thing is Bernstein-Sato. In fact, this is a fact in general, that f is smooth if and only if this bf function equals this. This is a theorem, I guess. Okay? So this is an example. The next example would be something like this. And you can repeat this game where I have and now I just hit it with this guy. And I get s plus 1 to the n. This is just a computation. So this thing is the BS polynomial. So these are two examples. Another example would be I look at the determinant of a generic matrix, generic square matrix. Let me call this out. I won't compute it, but here the BS polynomial equals s plus 1 times s plus 2 times s plus 7. In fact, I realize now I made a bit of an error, which is that I should have, when taking all these things about minimal exponent log canonical threshold, I should have been removing 1 with multiplicity 1 from this set. Maybe I won't say what this is, but somehow because s plus 1 is dealing with the smooth case, you want to remove a factor of s plus 1 to somehow model singular things. The reason I'm saying this is that if you know anything about rational singularities, you know that this hypersurface has rational singularities, whatever they are, and you can read that off this b function, because if I cover up these roots, all the roots are positive or numbers greater than, or negative numbers less than -1, which means the minimal exponent is greater than 1, which means it has rational singularities.
Can I just be confused about this?
Yeah.
So I thought you were running over all possible p's and then taking the generator of the idea.
Yes.
So maybe this is very stupid, I don't know, but like, so why, you took this one differential operator.
This is not a proof.
And you said, okay, this is.
So in this case, it's a proof because I picked one and it's as small as possible.
Yeah,
like it's either this or nothing. So this is one. It is actually not so obvious. Like you have to do a lot of work actually to check that this is in fact the BS polynomial.
Okay.
So all I've done is tell you that the BS polynomial divides the set. And in fact, if I actually give you the differential operator for this, it's still a lot of work to even compute this derivative. Yeah.
In general, is there some sort of even impractical but theoretically existing method to find this polynomial, or is it case by case?
So now you've hit to the next part of the talk, which is I was computing examples, and now we're done. Because there's basically no way to compute anything other than what I've written on the board. So this, what I've written here is easy, is equals on the board. And what's not on the board is, I would say, basically impossible. So I'm trying to avoid saying anything about D modules, but there is a program in Macaulay 2 that can compute this thing. But I mean, in practice, this thing will never return
but
anything.
in theory,
Yes.
it's possible.
I mean, I can give you an algorithm.
Yeah,
Yeah.
It is Turing computable, or maybe
It
not
is-
because that's complex numbers, but whatever.
There is an algorithm.
There's an algorithm.
Yeah, but in practice, it's useless. Okay? I lied slightly because I'm going to tell you the one case that's doable and falls in between easy and impossible. So I need to actually look at something now. Proposition. Yeah, I'm not going to write them all, but this result is due to many different people. So Yana, Lagrange, Cachet-Ward, Bellison, Maisonneuve, this is all like in the 70s or 80s. So let's say F is homogeneous and has an isolated singularity. Okay. Let me call the partial derivative this thing. This is an ideal in R. This is just the Jacobian ideal. So this is generated by all the partial derivatives of F. I can look at R, my partial F. Well, this is cutting out the singular locus. I mean, this includes F because I'm homogeneous. So this thing is defining the singular subscheme. I can look at R mod this thing. This is just cutting out a point because it's an isolated singularity. So this is some Artinian object that's graded. So I can observe that this is graded in Artinian, which is just to say that I can cycle through all the numbers that show up here. Right? This is the Milnor algebra, if you want. So with the setup, the result is then with the zeros, the Bernstein-Sato polynomial plus F, or minus 1, union So let me unpack this formula. I get minus 1. And then for every number that shows up in this graded Artinian algebra, of which there are only finitely many, I remember it. This should be an n, say. I put it here. I remember how many variables I have, and I get this fraction. And these are my roots. So if you know anything about Milnor fibers and this result I was saying about these eigenvalues of this Milnor fiber, somehow with homogeneous isolated singularities, this Milnor fiber is very well modeled by this ring. And so if there is some connection between this Milnor fiber and the roots of the B function, it's nice with such a result as this. So I'll say this is like 1979-ish by the people I just said. Okay, so that is the only case that's in between easy and impossible. There's a slight generalization of this that I will add, which is a definition. Suppose there exists coordinates x1 to xn such that f, maybe I'll phrase it this way. Yeah, I'll phrase it like this. Suppose there exists a grading on R, where R is C of all these polynomials, where I said xi, I give it the wi, and wi is some number strictly greater than 0. If f is homogeneous in this grading, so it's quasi-homogeneous. And I won't say it, but right, so the standard grading is I just give all the variables weight 1, but I could do some more other type of grading. I get some notion of homogeneity. It's not so bad of a grading because all my numbers are allowed to be positive. If they were negative or 0, weird things could happen. The same type of result holds in this setting of this quasi-homogeneity, where this will still be some graded thing, and I have to change my notion of n in degree a bit, but you can do this. Okay. So I think in the picture of the talk, or in the thing I wrote in the talk, I said I would first try to tell you what the B function is and tell you why you should care. I can't tell from the questions whether or not I succeeded in this, but I've given you a fake definition in terms of this, fuzzy thing with the functional equation, and told you its roots encode a lot of cool things, or at least things people think are cool, so they're probably cool. So maybe that's why you care. This is the second part I'm supposed to instill you with fear. So the fear is that first, these are the only examples I gave you, and they're pretty bad examples because they're somehow very incredibly restrictive. Then I told you this other result, and my contention is that's basically it. Like there are no other results out there, really, for computing these things. So let me try to justify the fear aspect in terms of a picture.
Wait, before you fill us with fear, can I ask you something? Like, this thing is stable under taking commons. Somehow, like, you could just take the same examples with more variables.
Yeah, that doesn't care about that.
Right?
It doesn't care about that. So yeah, I mean, this doesn't care about choice of defining equation. Those cone things doesn't care about that either. In the same way that log conical threshold doesn't care. Yeah. I didn't say this, but I mean, there's also local versions and there's analytic versions. So in practice, one has to work locally and define a local version of this, but I don't want to get into the sheaf theory to do this. I just want to pretend I have this funny definition of functional equation. Okay, so fear. Let's go through the cases that we can imagine. Let's say I'm a polynomial in one variable. Well, I'm going to let all my polynomials be reduced. All my hypersurfaces, I'm going to have these reduced varieties. So there's really only one option, which is my f is smooth. And then I know it's b function because the b function is just s plus 1. So we claim victory in C1, not so surprising. In C2, there's sort of two cases. If I'm reduced, I have an isolated, I have many isolated singularities, but there's some notion of a local b function where I can do things locally. So morally, I only have one singularity and it's isolated. And my singular locus, either I have isolated singularities, and there's two options, which is quasi-homogeneous and not. In this case, we're happy because that falls under the purview of this result. And in this case, you kind of just give up. So one of my colleagues, Ian Blanco, thinks about plane curves a lot in their B functions. And I've talked to him a lot, and my general sense is that the only set of data, numerical data you can give me, coming from this variety, that would tell me the B function is the B function itself. And there are certain ways you can sort of do these nice mu constant deformations, whatever they are. So sort of you can deform your plane curve singularity in a way that respects topological type. The B function doesn't care. It's going to change. So the B function is very subtle. And I think the general sense is that if you are in this case, this is incredibly difficult. And the idea of having a formula is not going to happen.
Can I ask you, is there like
Yeah.
a baby example, or I mean, maybe I don't know where you feel, like an example of a curve, plane curve singularity that is not quasi-homogeneous? Can you
Yeah, so let's say x squared plus y cubed plus so the only way morally this could be quasi-homogeneous is if I assign this guy weight 1/2 and this guy weight 1/3. And then if I do that here, this thing has to have weight 1/2 plus 1. And so these weight, this will be of degree 1 and 1 and not 1. Yeah, when you do these mu constant deformations, you can take something quasi-homogeneous and then add these terms to it in such a way that preserves topological type. The B function is going to be wildly different in a way that's not at all clear what the hell's going on. Okay. Hence the fear. So, okay, now we're in C3, and we're looking for something to do. We're looking for some math that we can do. Well, one case is I could say that I have an isolated singularity. And then we could say it's quasi-homogeneous and not quasi-homogeneous. In this case, I'm happy because I still have this formula. And in this case, if I can't handle isolated singularities in C2 that are quasi-homogeneous, I have no chance of doing it in C3. So this is basically impossible. So then I can ask if my singular locus, the singularities is one-dimensional, one-dimensional singular locus. And let's for the moment assume my thing is homogeneous. So if I have something homogeneous, I can look at the associated projective curve in P2. Locally there, things will look like plane curves. And I would maybe try to compute the B function at those plane curves. But I've reduced into this situation where I have this quasi-homogeneity and not quasi-homogeneity issue. So something I haven't told you, but the B function, it's sort of, you compute all the local B functions and then take their least common multiple. So I really have to know this behavior everywhere, like at every point. So if I can take something homogeneous, go inside P2, and it locally looks like something that's not quasi-homogeneous, I'm basically screwed again. Because I've ended up in the situation that I have no hope. And this is somehow just a step in the process, not even the whole process. So let me define something before I fill out this picture. Definition. F in R is locally quasi-homogeneous. Keyword here is locally, that's new. If locally everywhere, or maybe I'll say if for all P CN. There exists analytic coordinates such that the germ P is isomorphic to something like this, where G in R is quasi-homogeneous. Okay, this is kind of a definition that I've noticed people don't really like when I phrase it this way. But what I'm saying is that locally everywhere I can pick a defining equation so the thing looks quasi-homogeneous. So the prototypical example is if I take Z in P2, this thing will only have isolated singularities. I can ask if those singularities are quasi-homogeneous or not. Then if I look at the cone inside C3, this thing will be locally quasi-homogeneous. This is a very restrictive example because I'm imposing, this thing is also just truly homogeneous, but then it also has this extra thing. It's not the case that being homogeneous implies you're locally quasi-homogeneous. This is not a light condition. This is a pretty serious condition. So this is an example. Another example is A inside Cn is an arrangement of hyperplanes. So what do I mean by this? I'm taking a bunch of hyperplanes in affine space and looking at their union. So the defining equation of this thing will be a product of a bunch of linear polynomials. And you know, if you're in this union of hyperplanes, no matter where you stand, you look like a union of hyperplanes. So locally, it looks like a product of linear things that vanish at that point, which means locally it looks like a homogeneous polynomial. So this is an example. Other examples are, like the most general thing that I've never understood is like versal deformations of isolated complete intersection singularities, whatever these are. These things show up. But whatever, this is some condition where these are interesting classes of things. And if I return to this picture, I can say I'm locally quasi-homogeneous, and I'm not locally quasi-homogeneous. If I'm not locally quasi-homogeneous, I basically have no hope. Because either I have no this probably means I have no singularity property, no homogeneity properties at all. And if I can't handle a zero-dimensional singularity with no homogeneity properties, I don't have much chance of handling a one-dimensional guy. So here we've acquired the only place where maybe you could do something. All right, so this is essentially the context of the talk, right? As I put locally quasi-homogeneous things in 3 variables, and it's because of this picture. So you want to say something about B functions, this is somehow the only reasonable place to look. So let me focus on this case. So the paper this is based on talks about ranges of hyperplanes at the very end, but this is the easiest thing for the sake of talk, so let's just focus on this.
Can I ask you something?
Yeah.
So if I understand this, like you are extending, essentially stretching the gamma as much as you can so that you can still use this proposition from the 70s that you wrote down, right?
Except you can't use it. Well, I'm using it as an example of what the limits are. So if I can't use that, I cannot use that proposition here because I have to have isolated singularities. And here I don't have isolated singularities.
Mm-hmm.
But if I end up somehow in some local situation where I get to pretend my singularity is isolated, and I don't fall into the context of that proposition, there's no hope. If that answers your question.
But, I mean, my question is more like, what does smiley face mean? It means that you can compute as you did in your proposition, you can compute the full zeros of.
It means there's reason to think you could, not that you can.
It's like, it's not immediately clear that the proposition from earlier is contradicted.
Yeah, that's the thing. It's not immediately clear that you should give up. Yeah.
So then it should be more like a mathematical.
Yeah, it's like a maybe. It's a shrug.
Yeah, I mean, in this case, I'm happy because I have an equation. In this case, I'm happy because I have an equation. This may. And the point of the paper is yes.
Yeah.
Okay, so let's just talk about arrangements. Hyperplanes. Just remember, I'll use this notation, but this is just the variety of some f, where f is the product of linears. 2, 3, 1, guys. So let me tell you some results, I guess, which is, okay, I'll stick in C3. Well, okay, let me tell you some facts. If, let me say if the singular sub-C is cohomology, whatever that is, then the zeros of the B function are combinatorial. All right, so let me first say what I mean by combinatorial. I mean, if I'm an arrangement of hyperplanes, I can remember the ways all these various hyperplanes intersect. I get some giant poset. Data that can be read off that poset is called combinatorial. So I won't say too much about this, but in this case, this happens, that these roots are combinatorial. So I did this at some point. If A is tame, I won't tell you what this means. Then the zeros of this thing inside -1 to 0 are combinatorial. I won't tell you what tame is, but I'll just say that if A is in C3, tame is automatic. What I mean by these, I mean, you know, I have some polynomial ring Matsum ideal, given that it's a Jacobian ideal. And cohomology is some sort of algebraic condition. Tame is some other algebraic condition, but tame is very weak. I'll just say that I only know one example of something that isn't tame. But whatever, in C3, they're always tame. So if we're interested in arrangements in C3, which is what we should be interested in, then we know that the roots between 0 and -1 are determined by the way the hyperplanes intersect. So the question is, right? You talk about hyperplane arrangement people, they're very boring. They always have the same question, which is, can this thing, if you give me some numbers, are they functions of the combinatorics or not? So here are some numbers. I'm going to ask you if they're a function of the combinatorics or not.
Yeah. When you say the combinatorics, you take the complement and you put like a node for each connected component. Is this kind of?
So the sophisticated answer would be that the combinatorics of the associated matrix. But the naive answer would just be, I have a bunch of hyperplanes. Whenever hyperplanes intersect, I get a subspace. So if I look at all the possible intersections, I get a bunch of subspaces. Some of them are contained in others. That containment gives me a poset relation. I get a giant lattice, and I can remember the lattice. So if I can look at just that lattice and tell you some property, then that property is combinatorial. I mean, it's equivalently, I'm just saying that it's a function of the matrix associated with the hyperplane arrangement. So I will draw a picture, or try to. Oh, I should tell you the answer is no. So I'm drawing a picture in P2. Okay, so my lines are the hyperplanes. So these are 9 hyperplanes. And I want to focus on this one. I mean, these also intersect outside of it sometimes. Like for instance, here I have 2 lines intersecting. So this would be a double point, multiplicity 2. I'm not going to draw a vertex there. I'm only drawing vertexes at the triple points, where 3 things intersect. So maybe this looks like a classical picture, which is I have 2 arrangements. One where the 6 triple points are on a quadrant, and one where the 6 triple points are not on a quadrant. So if I give you an arrangement like this, these 5 points will give me a quadric. And if I move this guy around, this one point I shift it a little, sometimes it'll lie on that quadric and sometimes it won't. But as I shift it, I won't change the combinatorics, right? These hyperplanes, I'll still have the same like sort of data of ascending subspaces. So as I move this guy around, I will pass between this family and this family. And the quadric that contains all of these. So here, -2 plus 2 over 9 is the root of the DS poly. This was proven by Leuven in some Vinciano's paper in like 2015. And here it's not. I guess really he proved both. Walter told me that he told Morihiko Saito this, and Saito said some stuff he didn't understand, but seemed unhappy. And so then he disappeared for a while, and he somehow, using Saito magic, computed the B functions directly, and turns out this is the only difference. Right, if I compute the B function of this thing and this thing, they will be exactly the same, except one will have this root and one won't have this root. And maybe, where does this example come from? It comes from a guy, Ziegler, in like the 80s. Let me explain it so fast, so I'll just write it down. Oops. Okay, I'll explain this in a sec, but let me just say, this is some sort of statement about this object here. I've written as something that's supposed to model the case of an isolated singularity, where I had some Artinian graded object coming out of my Jacobian integral. But the point is that this is some algebraic thing, and in this case, there's something 0 and something isn't, and it's happening exactly at the degree of my arrangement -1, the number of hyperplanes -1. Let me tell you what this object is. Definition. Let's say M is an R module. M is the relevant ideal. And H0M of M, all the elements of M. Oh, this is a bad. Maybe I'll have N be more module. So this is the zeroth of the cohomology module of the relevant ideal. So I'm going to get all the elements in my module that are killed by sufficiently high powers of the maximal ideal. And this is basically set up in such a way that it's an Artinian guy, because it's going to be supported only at the maximal ideal. So this is some difference in B function, in fact, Taylor difference. It has this interpretation in terms of algebra. And then it also has this very provocative picture in terms of this quadrant condition. So this is the example of Antwerp. And low, that's long. So maybe I'll be a little cheat and say, yeah, I'll do two things. The theorem over me. Let's say A is C3 is an arrangement. And the theorem I'm going to write is that this is kind of the only thing that can never happen. So basically, all the roots are combinatorial except for that one guy. And that one guy is determined by this condition. Did I write it? I'll just have to remember. Then define A equals the QF for R. Then the zeros of BFS minus 2 plus 2 over the derivative, combinatorial. I don't mean this in an abstract way, in that I know through abstract nonsense that they are combinatorial. I mean, there's a formula I could write down that's very easy that exhibits them. And following that equivalent, minus 2 plus 2 over the degree is a root of the B function. And what do I need? I guess I need this to get up there. Okay, so this is the result. You could think of this in that, if I have these points on a quadrant, this is the special case, right? If I pick 5 points on a quadrant and then I pick another point, most likely it's not going to lie on there. This is the special case. So this is saying that this root shows up in the special case. Something I can prove, but I won't say, is that if you look inside the moduli space of hyperplane arrangements, if you fix a lattice and if you fix the combinatorics and look at all hyperplane arrangements realizing this thing, the set of hyperplane arrangements that don't have this as a root is Zariski open, which is analogous to this example, right? This is sort of the special case. This is sort of the Zariski closed statement. And so this is from last year. So you're supposed to now feel pleased because I told you a bunch of things that are scary from the 80s. Now I'm telling you something nice from the now. Yeah.
Is the idea behind this a little bit similar to this? That there's some sort of variety which captures some intersections or
No.
is it completely different?
So in fact, I would love to understand, every time I've heard someone talk about this example, they always say the stuff about the quadratic, and then maybe they'll say this thing or whatever they interpret that in their language, but they never tell me why those things are related. I would love to know the answer to that question. Because that is cool, and this is kind of arbitrary. And let me just give you a sketch of how this works. There's some DS module called fs for fs plus 1. These are differential operators by s's. They're acting on this. Somehow this module is encoding the b function. Specifically, it's the C annihilator, but it doesn't matter. What do? You compute x of this thing. I guess for this is not at all clear how to do this. I mean, these objects are super non-commutative. It's not even, I mean, well, this is very difficult to actually compute this x. It requires very natural results to even come with an initial complex to work with, but whatever, you do it. And then somehow you do this computation with all these spectral sequences and all these things, and you observe two phenomena, which is that these numbers always give roots of the DS column. So right, this thing here it was non-zero. That's because that number somehow is contributing a root to this guy. And in fact,
in general, or for hyperplane arrangements.
So this part is only for locally quasi-homogeneous in C2. So that's because I'm using this number, but you need this local quasi-homogeneity to get things going. I mean, as an example, like, okay, if I give you this guy and I ask you to compute a presentation of it, not even something I can use to compute a resolution, you're going to basically be screwed. I mean, you asked about computing this in Macaulay 2. This is what Macaulay 2 does. It tries to compute a presentation of this as a DS module, and usually it fails at that step. So something very special is going on that lets me do that here. And let me just add as a final thing that, just because I think it's cool, so maybe it's nice to say, which is somehow there's a symmetry in the zeros of this DS, of this polynomial, once I remove the roots coming from local cohomology. So you get a bunch of roots for free from this local cohomology data, and then if you remove those roots, there's a symmetry. And the symmetry is that these things are symmetric about -1 once I remove these roots. And so this gives you enough control that in the hyperplanar education, you just compute the thing directly. But these results hold without hyperplanar arrangements. It's just, you have a little extra going for you there. I definitely went too long, so I'm sorry. Thanks for listening.